Here we have this function of x, and it looks like this. So first we want to determine what is a maximum and what's a minimum. So when we look at this graph, we notice that at a there is a minimum value of the function, and here we have a maximum value of the function at b. Now, what does it mean to be a local maximum or a local minimum? So if we take b for example, here what we notice is that the value of the function at b is higher than the value of the function near the point b. When we say there's a local maximum at b, we are comparing the values of the functions near f of b, where f of b is the maximum of these values. And the same thing at the local minimum. Now, what we're gonna do, I'm gonna take these segments. So I'm gonna take segment A and put it in here. So A gonna be a minimum, and then I'm gonna take B and put it in here. And remember, B is a maximum. So first, what I want to find here, what's happening to the function of x, and then what's happening to the derivative of a prime of x. So first, I'm gonna split the function into two segments, so left and right. So on the left side, what's happening with the function, we see that the value of the function f of x are decreasing. Therefore, f of x is decreasing. And then what's happening to the function on the right side, it's increasing in value. Now what's happening to derivative? So when we think in derivative, again, think in terms of the slope of the tangent line of the curve. So on this side, when we draw a tangent line, the slope here is negative. Therefore, the derivative here is negative. And on the right side, when we have a tangent line, what we notice that the slope of this tangent line is positive. Therefore, the derivative there is positive. And lastly, when we draw a tangent line at the point B, what we notice is that the slope is horizontal, which means the slope is 0, which means the derivative there is 0. Now let's move on to B. So I'm gonna split that into two segments, left and right. So first, what's happening to the function f of x? On the left side, we notice the value of the function is increasing. And then we notice on the right side, f of x is decreasing in value. Now, let's think in terms of the derivative. So when we draw a tangent line on the left side, we notice the slope is positive. Therefore, the derivative there is positive. And then when we draw a tangent line to the right side, we notice the slope is negative. Therefore, the derivative there is negative. Now, when we draw a tangent line at the point B, we notice the slope is horizontal. That means the slope is 0, which means the derivative is 0. And always you notice here, we read the graph from left to right. So now let's think in terms of a critical point. What's the relation between a critical point and local maximum and minimum? So every time we have a local maximum or minimum, it's gonna be a critical point. So what's a critical point? So a point A, said to be a critical point, first it has to be in the domain of f. And then when we take the first derivative and evaluate it at a, it's gonna be 0. That means the slope at the point a is 0, or it's undefined. This is what's a critical point. And it can be given as a and then f of a, where a is the critical point and f of a is the critical value. So now if we have a critical point, we want to determine how we can determine if it's a local maximum or a local minimum. So there are two tests. We can do either test. The first test called the first derivative test, and the second test called the second derivative test. The first derivative test, we're gonna take the first derivative and equal that to 0 or find where it's undefined, and then we will find a point. That point called a critical point. So in this case, x is equal to a, where a is the critical point. So here I drew a number line. What I'm gonna do, I'm gonna take a value that is higher than the critical point, and then I'm gonna take a value that is less than the critical point, and I'm gonna plug each of these. I'm gonna evaluate them at the f prime of x. I want to know the signs of these values evaluated at the first derivative. Now if we go back in here, we can apply the first derivative test. We already know that a is a local minimum and b is a local maximum. So how we can determine by the first derivative test? Here at a, what we notice is that the derivative on the left side is negative and the derivative on the right side is positive. So we are going from negative to a positive. So when we go from the derivative from negative to positive, that means a is a local minimum. And here when we go to b, we notice that the derivative on the left side is positive, and on the right side the derivative is negative. So when we go from positive to negative, the point there gonna be a local maximum. Therefore b is a local maximum. So now the second derivative test, what we care about is the sign of double prime of x, which is the second derivative. So what we care about is concavity. So first let's look, what does it mean? What does concavity means? So this shape at a, this is called concaving up. This is concave up shape. And this shape at b, it's called concave down. So in terms of the second derivative, if we have a shape that concave up, the second derivative is positive, and with concave down, the second derivative is negative. So if we go back the second derivative test, what we will see is that we have determined the sign of the second derivative at the critical point. And here we have three possible scenarios. So first, the first derivative at a is 0, which means it's a critical point. And then of the second derivative at a is positive, which means it's concaving up, then it has a local minimum. The second scenario, we have a critical point, and the critical point evaluated at the second derivative is at negative, then we will have a local maximum. The third scenario, we have both the first derivative and the second derivative evaluated at the critical point is 0. The test tells us nothing. We have to do the first test. So an example in here, let's apply the second derivative test. So at a, it's concaving up. Therefore, the second derivative there is positive, which means a is a local minimum. Now, in term of b, since the shape concaving down, therefore the second derivative there is negative. Therefore, b is a local maximum. Now let's talk about inflection point. So its inflection point is where concavity changes. So if we go back to the function of x and we want to notice where is the inflection point. So again, it's where concavity changes. So we can go from concaving up to concaving down, or from concaving down to concaving up. So this at A, it's concaving up, and B, it's concaving down. So it's gonna be somewhere between these. So that's gonna be our inflection point. So again, inflection point is where the function of x changes in concavity. Now, how we find inflection point? A possible inflection point is where the second derivative is 0 or where it is undefined. To confirm it is an inflection point, we have to do a test. So what I'm gonna do, I'm gonna draw a number line. This x equal to b, it's the possible inflection point. I'm gonna take a value that is larger than p and a value that is less than p, and then I want to plug these value into the second derivative and see the signs of these. So if the signs changes, this is called an inflection point. If not, it's not an inflection point. Now I want to note here, this test is similar to the first derivative test when we want to find it's a local maximum or minimum. I want to note why is that? Because inflection point is actually a critical point of the first derivative. Why? Because when we draw a tangent line at the inflection point, it's gonna be the highest or lowest slope. That gonna translate to the highest value or lowest value when you graph the function of prime of x. Therefore, again, it's gonna be a critical point of a prime of x. Now we have this graph. I want to know where is the inflection point in here. So again, inflection point is where concavity changes. So first to determine the concavity, here it's concaving down, here concaving up, and here it's concaving down. Inflection point would be between concavity. It's gonna be here and it's gonna be in here.